An overload relay is typically mounted underneath a contactor, often having three prongs that go directly into the load side terminals of the contactor. We say it is coupled into the contactor. The combination of these two parts is called a motor starter. So when the contactor is energized, you have power coming in from the line side flowing all the way through the load side of the overload relay. On the face of the relay, you have the FLA dial, where you set the rated FLA, or full load amps, of the motor. This is where you define how much current the motor must draw for it to be considered an overload condition. This dial allows you to select between manual and automatic reset, and also serves as the reset button. And this is a trip test button. Then you have these two built-in contacts, a normally open and a normally closed. If the amount of current being pulled exceeds what the FLA dial is set to for a certain amount of time, it'll trip, which will alter the state of these two contacts. So let's take a look at this from the schematic perspective. Here we have a three-phase power circuit and a simple start-stop control circuit. And the overload relay is represented in both. In the power circuit, this symbolizes the heating element of the overload relay, and in the control circuit, we use the normally closed auxiliary contact. In this simulation, I'm using the color of the contact to show the present state, where red is closed and green is open. Since everything is in its normal state right now, the normally closed contact is red, while all the normally open contacts are green. So when I hit the start button, the contactor gets energized and closes the contacts in the power circuit, and the motor current is flowing through this heating element and to the motor. The higher the current, the hotter the heating element is going to get. Once it reaches a certain temperature, it is designed to trip, opening up the normally closed contact, de-energizing the contactor coil, and opening up the contacts in the power circuit and shutting off the motor. It's a common misconception to think that this portion breaks the power circuit, but there is always continuity inside the overload relay. We rely on the normally closed contact in the control circuit to open up, dropping out the contactor. The relay's normally open contact is optional. It closes on a trip and can be used to turn on a pilot light or sound an alarm whenever it's tripped. To reset the contacts after a trip, we can have it set to either manual or automatic mode. If we have it set to manual, then the reset button on the overload would have to be pressed first, and then the motor can be restarted by pressing the start button. In automatic reset, the contact will reset itself after a period of time after the trip, but in three-wire control, the motor will still have to be manually restarted as the starter coil remains de-energized. So now let's take a look at it from the mechanical perspective and see how it actually works. If we were to go inside of a bimetallic overload relay, it would look something like this. Now all of them are going to look a little bit different, but they all have these main components. This one was modeled after Eaton's XTOB. This box houses the normally open and normally closed contacts used in the control circuit. These prongs extend outside of the housing and they are coupled into the load side of the contactor, so that is where the current enters. Then the current flows through the heating element, which in the XTOB is wrapped around the bimetallic strip, separated by an insulator. Current makes its way through the strip and then exits through the load side. The bimetallic strip is made up of two different types of metal, hence bimetallic, and is designed so that as the heat from the heating element is transferred to the strip, they expand in such a way that causes them to bend. When it bends, it moves the black piece called a trip slide that is connected to the trip unit. Once it moves the slide a certain distance, it trips, and the normally closed opens and the normally open closes. So what may be surprising is the FLA dial, which lies directly in front of the trip unit, is in no way electrical. It's purely mechanical. When you turn this FLA dial to a higher FLA, it raises the tension in the tripping mechanism so that the slide has to apply more force to meet the trip threshold. So the question that arises, during an overload condition, how long is it going to take to trip? There's two different factors that play into that, and that is the amount of current flowing and the trip class setting. And we answer this question using what we call time current trip curves. This graph with a logarithmic scale shows time in seconds on the y-axis and current as a multiple of the FLA dial setting on the x-axis. We'll get to the trip class in a second. So if we have a motor that has an FLA rating of 100 amps and is constantly pulling 350 amps from a cold start, it's pulling 350% of what it should be, or 3.5 times as much. So we find 3.5, go up to the cold start curve, and it'll trip in about 50 seconds. By the way, a hot start is when the motor was started again after it had been running for a while beforehand. It's going to trip more quickly in an overload condition in this case because there is already some amount of heat in the bimetallic strip. Now in my example, the motor was pulling a continuous 350 amps, but motors don't always behave this way. The current can fluctuate. It may start off pulling 350 amps, then drop to the nominal 100 amps, then something causes it to shoot up to 200. To calculate the exact time that it'll trip in a case like this would be very tedious. The point I'm making is that these are not necessarily made for precision. These curves just give you a rough idea of how long it'll take to trip under a given circumstance. Now I mentioned that trip class plays a factor, yet you don't see it as a variable in this graph. And that's because each curve is defined by a trip class. This one I'm looking at now happens to be a trip class of 20. A trip class of 20 means that at a constant current that is 750% of the FLA current setting on a 1.15 service factor motor, the motor will not take more than 20 seconds to trip. So if we look at 7.5 times the FLA dial, we would expect to see it trip in less than 20 seconds, which it does. A trip class of 10 means that it would take less than 10 seconds to trip under those same conditions. The big takeaway from this is the lower the trip class, the less time it will take to trip. Here's an example where all of the trip class options are put on the same graph for comparison. The top curve, or the one that will take the longest to trip, is a trip class of 30. And this 10A that you will come across sometimes is a European standard, and it converts to somewhere around 7 seconds. And that is the reason you find its curve at the bottom. It will cause the motor to trip the most quickly. As for which trip class to choose, it's very application dependent. You want to pick one that's low enough to where it will trip soon enough to protect the motor, but if you have a motor that takes a long time to get up to speed and is going to be in an inrush state for an extended period, picking a trip class that is too low is going to cause it to trip before it reaches its steady state speed. For example, let's take a look at this industrial saw that has an 8-foot diameter, which could take several seconds to get up to speed. It not only has a high inrush to get it going initially, but it's also going to pull several times the FLA for the entire duration of startup. So if my trip class is 10 or 10A, I'm going to run into a problem because it's going to trip before it gets up to speed and can start pulling its nominal FLA. So choosing a trip class is all about finding a balance between these two factors, among other variables that may be specific to an application. That's pretty much it for the overload basics. Now I'll talk a little bit about the second type of overload relay, and that is the solid state, or electronic overload. And everything I've talked about is still valid. It's designed to do the exact same thing. It serves the same purpose. It just has a different way of sensing the current. It uses CTs and electronic circuitry instead of the mechanical bimetallic strips. This is a C440 overload relay. It has dip switches on the front that let you toggle between automatic and manual reset, as well as adjust the trip class. This is a nice feature to have, whereas in a bimetallic overload, the heaters have a fixed trip class. So if you wanted to alter the trip class, you would have to replace the heaters, if it even has that option. Here's the inside of a solid state overload relay. We have the 3 CTs, or current transformers, which is essentially a wire wrapped around a donut-shaped piece of metal. The motor current travels through the donut, which creates a magnetic field that produces a much smaller current through the CT wire, which is then connected to a circuit board where the signal is processed. While the new current is small, its amount is directly proportional to the larger motor current, so it knows exactly how much current the motor is pulling. Because we have electronics that can process this information digitally, another big advantage to solid state is you can add communication modules, such as Ethernet or DeviceNet, and monitor different parameters for use in an automation system. So you get a lot more flexibility with the solid state, but of course you will pay a little bit more for it. So if you don't need these extra features and/or have a clearly defined application that is never going to change,